All right, calculus, here's number 3. This is a table problem. You're going to see a table problem almost every single test. So if this is something that's hard, we did a day like 11 or 12, something like that was on table problems. So let's do these 4 chunks. Step 1, approximate it using a tangent line approximation at t equals 5. Anytime you see tangent line approximation, we're thinking y minus y1 equals m times x minus x1. There's our tangent line. We need to come up with the equation and then plug in 5. So really, instead of x and x1, maybe we should use t and t1. It doesn't change things. It'll give us the same result, so we're good. But we use the stuff from the problem here. So it says, if I'm making this at t equals 5, then my slope, h prime, is 0.7. My time is 5, and my depth is 6. So my depth is 6, that's my output. My slope, 0.7, that's h prime, right? That's in the table. And then my input was 5. There's my tangent line, and then it says approximate it at 4 minutes. So that's going to be the t value I plug in. So y minus 6 equals 0.7 times 4 minus 5, that's negative 1. Negative 0.7, then add 6, so y equals 5.3. This is our approximation. So that's the approximation of the height at 5.3. But if we're asking about whether it's greater than or less than, we actually only care about concavity. So we're trying to say, is my function concave down? And in that case, my line will always be above the function. Or is my function concave up? Because if that's the case, my approximation will always be below that function. And that's usually either told to you or you have the tools to find it. And in this case, it's told to us. The problem says, during this interval, h double prime is greater than 0. That means it's concave up. So since it's concave up, my line is always under, so it is an underestimate compared to the true value. So is my estimate greater than, I would say the estimate is less than. Since h of x is concave up on the interval. Is it an interval? Yeah, on the interval from 0 to 15. This is probably 3 points, probably 1 point for making the line, 1 point for using it, and then 1 point for having that estimate with the reason. Part B says, find the rate of change at 2. The rate of change of volume, excuse me. So this is actually a related rates problem, like what we did on Tuesday, April 15th, on tax day. There you go, Mr. Desrich. Step 1, write an equation. Volume equals length times width times height. But in this case, length and width are actually always the same. So my tank, is always 10 by 20, but the height is the only thing that's changing. So I'm going to rewrite this. My volume function is 200 times h. But I want to know, how is my volume changing? So we're going to take a derivative with respect to time. Anytime it says rate of change of the volume, and it gives you a specific time, we're thinking derivative of volume. We're thinking, how is my volume changing? And I don't have any dv dt values. I just need to do some related rates to it. So derivative here, dv dt equals 200 times dh dt. And at t equals 2, let's look back at our table. H prime is the same as dh dt. My output here is 0.5. So dv dt evaluated at t equals 2 is 200 times 0.5, or just 100. 100 what? It says indicate units of measure. I can always find my units based on reading this out loud. It says change in volume over time. So So what's a volume unit? In this case, my volume units are inches cubed. So it's inches cubed per time, so change in volume over change in time. My time was minutes. Cool, that's it, we're done. Probably 2 points on that one. Third one, use the left Riemann sum. This isn't anything too crazy, and again, you don't even have to evaluate. Left Riemann sum, remember, delta x times the height. So I'm going to zoom out so I can see both of these at the same time. Delta x for the first chunk is 2. The left side of that is 0.4. Plus, you know, I'm actually going to add something here. I'm going to say my integral is approximately equal to that. This isn't necessary, but I think it is valuable to say, like, this is what I'm finding. This is what I'm actually evaluating here. So delta x times the left interval plus delta x times the left side of the interval again, plus delta x times the left side of the interval, plus delta x times the left side of the interval, plus delta x times the left side of the interval. Do I need to evaluate? No, don't even think about it. But this is tricky if you don't have a number. So you can evaluate it if you want. I'm not going to. But it says explain the meaning. What does this mean? This means if I'm integrating a rate function, that's a total amount. I know I tried to really hammer that into our brains here. So what does that mean? That means the height has increased by that amount from t equals 0 to t equals 15. This is the increase in height of water in the tank. Water in the tank in inches, right? Because it says indicate units, from t equals 0 to t equals 15. Anytime we integrate a rate function, we integrate a derivative, we get a total amount. That's our key idea here. This is probably 3, maybe 4 points, because you got to do the Riemann sum, you got to say what it means, and there's just a lot of ways to go wrong here. So 3, potentially 4. And then the last one, is the approximation greater than or less than? So this is a question I've asked you before. For left and right Riemann sums, we're trying to decide whether my function was increasing or decreasing. So look back at your table. It tells us that it's concave up, but also these are always going up. These are always increasing. So imagine I have an increasing function and a left Riemann sum. This is always going to be under the function. So is my approximation greater than or less than? It's less than. There's going to be extra space that I haven't counted for, because h prime of t is increasing. So less than the actual value, since h prime of t is strictly increasing. Strictly increasing just means it never stops to decrease based on what we can see on the interval from 0 less than t less than 15. That's all we got to do here. This one, table problem, definitely one we should be able to do. Hopefully that went well. Nice work.